Okay. Now I'm recording and it can hear me. I'm going to share my screen. Boom. Okay, great. Thank you, Angel, for saving the day. Let's give her a round of applause. Thank you. Yes. What? Yes, it should be under the modules. Thank you for asking. Let's go to the internet. If you go to modules, if you scroll down to chapter 6, oh, it still didn't publish. I have clicked published on this multiple times. And I unpublished other things on here because it will confuse you. I literally just did this. I don't know what's happening. Okay. Okay, good. I'm glad. I'm going to unpublish these things because they're not helpful to you. Okay, thanks for asking. Sorry about that confusion. Leave this this link for later. It's just to get practice problems, but I think it'll be confusing until you can tell the difference between which one. You don't need this group work key because your group work is going to be different. Okay. That should be everything. I don't know why I literally just did that. Okay. Anyway, thank you guys for helping me. So is that good? Are there any other questions? You have everything you need? Okay, great. I didn't sleep very much last night. My friend got into the airport at Love Field, which is so far away, really late, and then her flight got delayed. So I went to bed at like 1:30 or 2. And I woke up at like 6:30. So brutal. Okay, so one is sucrose, one is sucralose. The difference is that alcohols turn into chlorines. What about the stereochemistry? Are any of these circled places stereocenters? Yes. Which one is a stereocenter? The one on the left, the middle, or the right? The one on the left is a stereocenter. Why aren't these two stereocenters? They have 2 hydrogens on them. So there's only one stereocenter here. It's this alcohol. It's on a 6-membered ring where one of the carbons is substituted out for oxygen. So if you followed all the way around the ring, you would get a point of difference. So there are 4 different things attached right there. So remember we talked about how enantiomers, they play out in medicine, but also because this is an opposite enantiomer just right there at that one chiral center, sucralose can't be digested by our body, but sucrose can. Wild, right? That's how artificial sweeteners are 0 calories. Okay, the other thing though that's happened is these are substitution reactions. So we've swapped out the alcohol for the chlorine, and that's all about, that's what substitution reactions are, is we're swapping out one group for another group. It's a substitution. We're making a switch. So that's what chapter 6 is all about. We're going to learn about substitution reactions. We're going to learn the mechanism of them. We're going to determine what the best reagents are for them and how to improve the rate and the yield. And the rate means like the speed, and we also call it kinetics. And we're going to use a lot of things you've already learned from the last 5 chapters. We're going to talk about hybridization. We're going to talk about functional groups. We're going to talk about nucleophiles and electrophiles. Do you guys remember what those are? What are they? Nucleophile has extra electrons, electrophile lacks electrons, and what specifically they do that makes them different than Lewis acids and bases? That's true, but they do something. There's an end product of these two when they come together. They form bonds. Who said that? Yes, they form bonds. So they form bonds that makes them different than the acids and the bases. The acid bases don't necessarily have to form bonds. Electrophiles and nucleophiles are forming bonds, but they are also Lewis acids and bases. We're also going to use stereochemistry. You saw the change of stereochemistry of that one point on the sugar molecule. Curved arrows, you're going to have to be able to show how the electrons move. We also call that mechanism, using the curved arrows to say, why does this happen and how does it happen? You're going to need to know about resonance structures and a lot of else things that we've already learned. So yay, you're putting all the stuff you've learned for the last 5 chapters into practice now. Okay, so big ideas I want you to take away from this chapter. You need to know substitution reactions. You need to be able to predict products, rate laws, stereochemistry of those reactions, and you need to be able to understand reaction coordinate diagrams. We're going to practice those in recitation tomorrow. These are the types of concepts that you'll see come up on your quiz. And then I'm going to just do a brief overview of the chapter for you because I think this part can get kind of confusing because substitution, there's Sn1 and there's Sn2, two different types of substitution. And I just want you to kind of have a roadmap. So we're going to come back to this slide over and over through the chapter so you can kind of see where we're at. So this is our roadmap of the chapter. So first, we're going to look at the overall reaction, what a substitution reaction is. That'll be like our 2-minute summary that someone asked for on their one of the forms you guys filled out for me. You're like, give me a 2-minute summary. Overall reaction, 2-minute summary. I'm going to tell you what all the pieces of the substitution reaction are that we need, what all elements need to be present. Then I'm going to give you a brief overview of the two different types. One is like happens all at once, and the other is 2-step. And so we're going to talk about why there's 1-step and 2-step reactions. And then we'll dive deep into each one, 1-step and 2-step. And then there's a little bit extra that we'll get to at the end of the chapter. So let's start with overall reaction. So your 2-minute summary. You start with, usually it's an alkyl halide, but anything with a good leaving group. And it's called a leaving group because it's the thing that leaves to get substituted out for something else. So you need some kind of electrophile with a good leaving group. And then you need an attacking group that can come in and take the place of the leaving group when the leaving group has left. So literally you're swapping out your leaving group for your attacking group. That's the very brief overview of a substitution reaction. What questions do you have about that? If any. Okay. So what's the nucleophile here? And what's the electrophile? You can just shout it out. Nucleophile is the attacking group. So then what does that make the electrophile? The one with the leaving group, yes. So the bond actually forms not to the leaving group, but to whatever the leaving group is attached to. So overall, we call that the electrophile. So the nucleophile is the attacking group. You'll hear me call it both of those things. An electrophile has the leaving group, and that's sometimes called the substrate. So leaving group, electrophile, the thing with the leaving group on it, substrate, those all mean the same thing. And then nucleophile, attacking group. Sometimes they're also called bases, but that's not really the most appropriate thing. You want to call it a nucleophile because it makes the bond. So that's different than being the base, right? Okay. So your overall reaction, this is called, I'm going a little bit deeper into it. It's called a nucleophilic substitution. The reason it's called a nucleophilic substitution is because the nucleophile is trading out for something else. So you're swapping the nucleophile for something else. So nucleophilic substitution. So sometimes you'll see the S with a little N. That means substitution nucleophilic. That's why it looks like that. The nucleophile is going to donate an electron pair to the substrate. And then the bond between the carbon and the leaving group breaks. And so the leaving group, in this case, it's the X, leaves with electrons. So it becomes X minus usually. And the nucleophile typically starts off with an excess of electrons. It can be neutral or negative. If it's negative when it bonds, it becomes neutral. If it's neutral when it bonds, it becomes positive. Just like if water takes on a proton, it becomes hydronium. And then so your nucleophile, these two electrons make this bond. And your substrate loses the leaving group, and the leaving group takes the electrons from this bond with it. So the carbon ends up with the same number of bonds. And then I do want to note, although we will talk about this more later, with substitution reactions, the stereochemistry can change. So here you see that this stereochemistry has changed, and we also saw that earlier on. But how it changes depends on what kind of reaction it is. We already talked about the Lewis acid space. Okay, so there are two different mechanisms by which this happens. One is all in one step, and this is called an Sn2 reaction. I know that that is stupid. It happens in one step, it's called an Sn2. One step is an Sn2. The two is because there's two molecules involved in that one step. I would like it better if it was called an Sn1, but that's not how it works. So we have to go with what it already is given to us as. So one concerted step means the nucleophile attacks while the leaving group is leaving. It happens sort of all at once in this like smooth transition. And then you have your substitution. There's two separate steps where the leaving group leaves and then the nucleophile comes in and forms a bond. So those are your two options. The two separate steps is called an Sn1 because one molecule is really the deciding factor on how quickly the reaction happens. And we'll talk more about that when we do our deep dives, about why they're named what they are. Okay, so let's talk about the anatomy of the, actually, I'll go ahead and give you my barstool analogy now. Okay, my favorite analogy for these two things is if there's somebody at a bar and then there's somebody who wants their seat. Okay, so if I'm sitting here just chilling and somebody wants this seat, two things can happen. They could push me out of the seat and take it, which would be rude. Or they could wait for me to vacate the seat on my own and then come in and take it. So either it happens all at once where they push me out and take my seat. That's something that a sibling would absolutely do to you. If you have siblings, I could just picture my sister doing that to me. Or they could wait for you to leave and then they'd come in and take your spot. So those are kind of the two different reactions. I call that my barstool analogy. These are our two reactions that we're looking at. The one where somebody pushes the other person out, it happens all at once, and then one where one person leaves and the next person comes in. So the pieces that we really need for this to happen is a good leaving group. Usually this is a polarized bond, so a lot of times you'll see them as chlorines, bromines. Those are the two big ones. Sometimes iodine, fluorine, not as much, I think, because it's not very stable after it leaves as F-. But because it's already so polarized, and it already is pulling so many electrons towards it, it's not giving much to that molecule anyway, right? Like it's kind of moved on. It's 1 foot out the door, and so it's kind of not that big of a deal for it to leave the rest of the way and something else to come in and take its place. And then after it leaves, it needs to be stable. So fluorine is a very polarized bond, but F- is not a very stable atom. We don't see a lot of F- ions floating around, right? That's because it's not very stable. So fluorine's not a great leaving group, even though it's very polarized because it's not stable after it leaves. And then we also want it to not be too sterically hindered, or we want it to have the proper substrate. So it kind of depends on which type of reaction. I should have said not sterically hindered or substituted enough. We'll talk about that. And then you also need a nucleophile. And this can either be negatively charged or neutral, but it needs extra electrons to be able to make that bond. And that's going to form a new bond where the leaving group has left or as the leaving group is leaving, depending on the type of reaction. Okay, so let's start with a good leaving group. Here are some examples of good leaving groups. I gave you it on the top row. This is like if it was already still bonded to the carbon, right? So like if it was part of the alkyl halide. And then after it's left, this is what it would be. So if you have H3O plus, that's a good leaving group, right? Or if you have, because once it leaves, it's just water. Or if you have ammonium and it's able to leave and form ammonia, did I get that right? I think it is. That's a good stable group, right? That's a neutral molecule. It can function on its own. So good leaving groups are usually pretty polarized, and then they also are pretty stable after they leave, and you can see that in all of these groups here. And this just kind of shows you as the leaving group leaves, you want to see that polarity, and that strong negative on the leaving group is part of what makes it comfortable departing. Alkyl halides are a good one. They're very polar. Their halogen ions are typically stable except for fluorine, and so they tend to undergo substitution reactions. So here's kind of an example of what you might see: a primary alkyl chloride, a secondary bromide, a tertiary iodide. All those are good options for a good leaving group. All of these could undergo some kind of substitution reaction. Okay, these are not alkyl halides. These are alkenyl halides, or called vinyl halides. They're not sp3 hybridized, so they're sp2 hybridized, the reaction won't work. Same thing with aromatic rings. You need an sp3 hybridized carbon for this to work. It won't work on an sp2 hybridized carbon. Dr. Berhay talks about this every semester. He emphasizes it every semester, and every semester he puts on his test a substitution reaction with a vinyl halide, and every semester everyone gets it wrong because they don't pay attention to this detail. So pay attention to this detail because I'm very likely to do something similar. Okay, and then alkenyl halides are also called acetylenic because acetylene is the basic carbon-carbon triple bond. They also are not alkyl halides, and they also cannot do substitution reaction. Okay, so then we also, that's a little bit about a good leaving group. You'll see more of these as we go through. I'm just giving you the overview so that you know all the information so that we can do the practice problems later. It's going to be a lot of me talking today, which is kind of a bummer, but I don't know how to get around it. But you'll get to do lots of practice problems later. Okay, so a nucleophile is needed. And a nucleophile just can form a new bond where the leaving group has left. So for good nucleophiles, you need extra electrons. It can be a strong nucleophile. A strong nucleophile is one that's negatively charged. And a weak nucleophile is usually neutral. So remember I said it can be negative or neutral. As long as it has extra electrons, it can still attack. Okay, so here's a quick practice problem before I keep lecturing at you. We're going to dissect the anatomy of this reaction. So I want you to label the nucleophile, label the electrophile, slash substrate, circle the leaving group before and after it has left. You don't have to do curved arrows yet. We're only doing the anatomy. You're dissecting this. You're not showing the mechanism. I think most of you guys have finished up. So what's the nucleophile? The OH minus, you can say hydroxide if you want, but don't let that confuse you because hydroxide is not what it's called if it's neutral in the nomenclature for IUPAC, right? And it's called OL. So I usually just call it an OH minus. It's going to be the thing that attacks. That's the nucleophile. And then what's the electrophile slash substrate? What's the name of this? How many carbons are here? 2. So what's that? And then there's a substrate or a substituent. What's that? So 2-chloroethane. That's what I'd say, or just chloroethane, I guess. This is something. Yeah, chloroethane, not 2. Yeah, I'm sorry. I was numbering it wrong. Okay, chloroethane is the substrate. What part of that is the leaving group? The chlorine. Okay, great. So And you can see the chlorine gets swapped out for the alcohol. There's no change in stereochemistry in this reaction because it's not a stereocenter. Yes.
Because there's like two types of reactions, right?
Yes.
Or something that
Mm-hmm.
the base spontaneous be the one where it's
We'll get into that on our deep dive. Right now, I just want you to get on board with the language that I'm using so that you know what I'm talking about as I get into the deep dive. So that's why I'm starting with this, the anatomy of it. And then I'll answer your question. Yes.
So for the one that, so if this chlorine is dropped in the substrate, would not automatically be the leader?
Yeah, the thing that gets swapped out is the liquid. The thing that gets replaced is liquid. Yeah. You're welcome. Any other questions? Okay. So now we're going to switch to going over the answer to your question, the mechanisms of the two types of substitutions. So the first one I'm going to go over is the one that's all in one step. And this is primarily determined by there being a strong nucleophile. There's a few other factors, but if there's a strong nucleophile, then it's going to probably favor the one-step reaction. And if we go back to the bar stool analogy, if I'm sitting here and I want this seat and there's some jerk who wants to take it, it's going to be a strong jerk who is able to physically push me out of the chair if I'm like holding on, right? So if there's somebody strong, he'll be able to push me out of the chair and take it. But for the next one, it'll be the weaker nucleophile, but we won't talk about that yet. So strong nucleophile typically favors this. Okay, and it happens where the strong nucleophile will attack at your carbon, and that is the driving force for the leaving group to leave. So as those as the electrons push in towards the nucleus, then the already polarized fluorine bond on the other side is happy to leave. It's like, fine, I'm already one step out the door, I'm fine to leave. So another way you could think about this is if you're in a relationship, I feel like I already used this analogy, but if you're in a relationship and some new guy's coming in to take your girl and the guy who's already there is like, fine, I didn't really like her that much anyway, it just leaves. That's what's happening here. Someone comes in, makes a move, and kicks the other person out. Okay. There is something called a transition state, though, as this is happening. So a transition state isn't a intermediate. It's not something you could bottle and put on a shelf. It's just as one bond is forming and the other bond is leaving, there's temporarily this transition happening. So while it's in transition, we call that the transition state, and that's the highest point of energy that you have to overcome to be able to make the reaction happen. Okay, so in this case, your alcohol bond is alcohol to carbon is starting to form, and your bromine carbon bromine bond is starting to break, and then ultimately you get your new methanol plus your Br minus. That's plus Br minus, as in you get both of these, not like this bromine is positively charged; it's negatively charged. Okay, so all in one step. And then the two separate step reaction happens where the leaving group leaves on its own. So that would be if you have a weak nucleophile that's not strong enough to come and push somebody out of their bar stool, the person decides to leave their bar stool on their own, and then somebody comes and takes their seat. And your question, I think, was, does this happen spontaneously? And I don't know if spontaneously is the best way to put it, because it is a very slow step reaction. This is like going to take a long time because it does leave a carbocation behind, which is not the most stable. But it's already so polarized that it's not a huge change to go from the bond to not having a bond there. So I think it's more like it's in equilibrium, and while it's away, that's when the nucleophile comes in. Like if I'm leaving my bar stool coming back, leaving my bar stool coming back, and then at one point when I'm gone, somebody sees the opportunity and takes it, that's more like what happens than thinking of it as like spontaneous. Does that answer your question? That's kind of how I envision it, because it's not energetically favorable for that bond to break. It's just already pretty close. And so I think in equilibrium, sometimes the electrons are closer and sometimes they're farther away. And when they're further away, that's when the weak nucleophile can come in and make a new bond. So the way we represent that, and you also kind of have to remember, I guess, when we do mechanisms like this, we're doing our best to put on paper something that happens at the molecular level. So it is a lot more complicated than just like, oh, the leaving group leaves and a new thing comes in. It's like everything's constantly moving, electrons are moving, things are in equilibrium, bonds are breaking, forming all the time, you know, so there's a lot going on, but we try to simplify it down just to the major steps that will determine the outcome of the reaction. And we know what the outcome of the reaction is based on experimental steps. So this first step is the leaving group leaves. The alkyl halide is so polarized, it takes its electrons with it and goes, and then it leaves behind a carbocation. This step is hard energetically to achieve. So they call this sometimes the rate determining step. So the leaving group leaves and you get your carbocation, and then your nucleophile, which is weak, it was not strong enough to kick the other thing out, so it has to wait until the carbocation is formed, comes in and forms a new bond, and usually because it starts out as neutral, if it gets a new bond, it becomes positive. So you can see this oxygen started out with a neutral formal charge. It has 4 electrons and 2 bonds, adding up to 6, which is what its valence electrons come with. And then over here, you can see that it has one of its lone pairs became, I think that'll show you the arrow, became the bond between the oxygen and carbon, leaving behind only 3 bonds, 2 lone pairs. That's why it's positively charged. So that's your formal charge coming in. Okay. So then barstool stealing bully, that's my analogy to help you remember it. A strong bully will push you out of your bar stool and take it. That's an Sn2 reaction. A weak bully, or someone who doesn't have the strength or who doesn't have the boldness maybe to come in and just take your seat and push you out, will wait for you to leave and then steal it subtly. That's what I think of for substitution reaction. If you can think of other analogies that help you, like a girlfriend-boyfriend analogy or something like that, whatever analogy works to help you remember is fine with me. But the Sn2 is the one-step reaction because it has 2 molecules involved in it. And in that transition state part, the high energy point. And that takes a strong nucleophile. And then the Sn1 favored by a weak nucleophile, that is the 2-step reaction, but it's called a Sn1 because there's only 1 molecule involved in the high energy point when the leaving group leaves. So that's why we named them Sn2 and Sn1. Okay, so that's the overall reaction. That's the mechanism of the 2 types of substitutions. And now we're going to deep dive into an Sn2 reaction and an Sn1 reaction. Do you have questions for me? No questions? How are you feeling? Are you just like overwhelmed with all the information I'm giving to you? A little bit? Does somebody want to just take a stab at like summarizing what I said again? So it's called a teach back. Just so I can make sure that y'all are tracking with me. It doesn't have to be perfect. Okay, go for it.
In the Sn2, that's where the one coming in is strong enough to push it out.
Push the leaving group out specifically.
Out of substrate. And then the Sn1, that's where it's like a more polar bond. And so one side kind of leaves on its own, and once that intermediate has happened, another group can come in and take the bond.
Perfect. Do you guys agree with that? Do you feel like you're tracking to some level? If you feel like you're tracking at some level, do this for me. If you're like, oh, maybe, and if you're totally lost, do it down. Okay, nobody looks totally lost from what I see. So I feel like this is a good place for us to keep moving forward. Okay, so I'm going to deep dive into the Sn2 reaction. I'm going to start this today. We'll finish Sn1 and Sn2 tomorrow, and then we'll get into elimination reactions before your recitation. I already sent your recitation stuff to be printed, so if we don't get all the way through eliminations, you can just do what we get to in recitation. Okay, so when we do our deep dive, we're going to look at the stereochemistry of this reaction. We're going to look at the kinetics and a little bit more of why it's called Sn2. And then we're going to look at the reaction coordinate diagram, also known as the free energy diagram. Does that ring a bell? Reaction coordinate diagram, free energy diagram, vaguely from Gen Chem? Some of you? Okay. So for some reason, we like to use the phrase backside attack in organic chemistry. It causes an inversion of the stereochemistry because the nucleophile in an Sn2 specifically attacks from the backside, the opposite side of the leaving group, and it inverts the stereochemistry. So the nucleophile attacks, the leaving group starts to leave, there's a transition state, and because both of them are present during that transition state, one has to come in from the opposite side. If they were in the same side, that would be too sterically hindered, right? They wouldn't be able to do it. There'd be too much. Do you know what I mean when I say sterically hindered? Okay, sterics is just like the bulkiness of the molecule. So something is, and like stereochemistry is the RNS configuration. So it's really the 3D arrangement. So sterically hindered means the 3D arrangement is big and in the way. So a big group that's really bulky, like a tert-butyl group that has all those carbons around it, that has a lot of steric hindrance that's hard to get to because of all the things around it. So it's really just like, it's cluttered. Okay, so it would be too cluttered if it came in from the same side as the leaving group while the leaving group's also trying to leave. That would be really hard. So it's easier to push it out from the backside. And then at that time is when your stereochemistry begins to invert. If you can imagine, you know, a tetrahedral bond. Oh, I meant to have this up. I can show it tomorrow. A tetrahedral bond, and then it shifts into that trigonal bipyramidal, where there's like 3 in the plane and 2 sticking out. And then one side of the trigonal bipyramidal leaves, and it shifts back into your tetrahedral 3D arrangement. So that's why there's an inversion of stereochemistry, assuming that the nucleophile and the leaving group are both the highest priority molecules. Usually they are. So it converts from R to S. So if you think back to that sucralose example, and we saw the inversion of the stereochemistry at that 1 carbon, that tells me that there's probably a backside attack, and there's this inversion of stereochemistry. It went from R to S. So it'll switch from R to S or vice versa. Okay, and this is just kind of an orbital view of that same thing where the nucleophile starts to come in and attack. You don't have to worry about the antibonding orbital. It'll come in and attack here, and then it pushes the leaving group out. And you can kind of visualize like that's why the stereochemistry is inverted, because now there's a higher electron density on one side than there used to be. So over here, there's not much electron density. Over here, there is. After the transition, the high area of electron density has switched. Okay. So this is just showing you again, it inverts the stereochemistry. Backside attack goes from R, if you actually want to calculate it all out, to S. And then in a ring, I don't know why this is animated that way. I edited the slides, but I always miss something. The nucleophile will attack from either if you have a ring, you know, and you could imagine one pointing up and one pointing down, the nucleophile will attack from the opposite side. So if the leaving group's on the bottom, the nucleophile will come from the top and kick it out. And now the nucleophile would be the wedge, and the stereochemistry would have been inverted, or vice versa. So if this I is a dash, and then your OCH3 comes in and attacks, it kicks out the I, and now the OCH3 is a wedge because the stereochemistry inverted. It came from the top and kicked out the thing on the bottom. So this is just giving you a lot of different examples of that. Okay, and then we talked about also the stereochemistry of sucrose and sucralose. Right here, you know, is where we saw the change. So it's very likely that because of that inversion from pointing down to pointing up, that this is an Sn2 reaction. Okay, and then we also want to talk about the kinetics of the reaction, because as a chemist, I want to be able to make a reaction happen quickly and easily, right? So when I think about the kinetics of the reaction, in this case, the reaction depends on both the nucleophile and the leaving group, right? That rate determining step, the transition state where it's really high energy, is made up of both the nucleophile attacking and the leaving group leaving, so both molecules are involved. So you don't have to do any math in terms of finding the rate law, but the rate is equal to The equilibrium constant and both the nucleophile and the substrate are involved in the rate in equal amounts. So rate equals, sometimes it's written like this, K, which is the equilibrium constant, I think, times substitution, or the substrate and the nucleophile. This is a second order reaction because both of those are involved. So it's called bimolecular. You had to learn how to calculate second order reactions way back in Gen Chem. And that's why it's Sn2, because it's bimolecular second order reaction, because two things are involved in that transition state. So even though it's all one step, because the rate depends on two things, because it's a bimolecular reaction, it's a Sn2. So substitution, nucleophilic, bimolecular. That's what Sn2 literally means. So the rate of reaction, they'll say, can be measured by both the consumption of the reactants or by the appearance of the products. Those will happen at equal rates. You don't need to worry about that too much. Okay, and this is just to show you that this old chart that you saw in Gen Chem and you've probably completely forgotten about. If I double the rate of, or double the concentration of this substrate, then the rate overall will double. If I double the concentration of the nucleophile, then the rate overall will double. If I double both of them, the rate overall will quadruple. So the rate is dependent on both of them. What happens if I cut one of them in half? What do you think it does to the rate? It halves it. What if I cut both of them in half? Goes by a fourth. And also, you can alter the concentration by changing the amount of solvent. So if I cut the amount of solvent in half, that doubles the concentration. If I double the amount of solvent, that halves the concentration. That question comes up a lot on the ACS exam for whatever reason. Okay, I'm going to finish this up and then we can stop. So the rate of reaction, again, is proportional to both the concentration of the reactants and of both reactants, substrate and nucleophile. When either is doubled, the rate is doubled. That's why it's second order. And that's why it's Sn2. Substitution, nucleophilic, bimolecular. S for substitution, N for nucleophilic, 2 for bimolecular. And then here's the reaction coordinate diagram for this. So we'll start at this is an example that is, that has a negative free energy change. So it's thermodynamically favored. These are more stable. The products are more stable than the reactants. The nucleophile will attack. The leaving group leaves, and the transition state is the highest energy point because it's hard for that transition to happen, right? There's a lot of electrons really close together. That's not stable. That's unstable, meaning high energy. So this is high energy. You have to be able to overcome this energy to be able to end up with your products, which are ultimately more stable because it's less polarized. It's a more stable reaction. So the reaction coordinate indicates how the reactions progress. So it's just showing you how the energy is changing as the reaction goes from reactants to products. Yes. I think it can. I won't ask you a question like that. Usually reactions are going to favor the side that's more stable. So if the overall equilibrium favors one side or the other, it's usually the more stable side. So if the reaction has the larger equilibrium arrow towards that, you know, it'll be usually more energetically favorable. Sometimes, however, if an activation energy is easier to overcome for one than the other, it'll choose the less stable products if there's like two options. But we don't have that case here. But sometimes like a reaction can go one or the other pathway, and the less stable one might have a lower activation energy, and then the more stable one, you have to put more energy in. And so that's kind of the only time I think of that. It's very relevant. That's a good question. This is also sometimes called the free energy diagram. So the transition state is here at the top of the curve. And then you can see the energy difference here shows the difference between the reactants and the products. So overall, the products are more stable. So you should be able to label where the products and reactants and everything goes on this. And we'll practice it during recitation tomorrow, but you can also practice it today if you so desire. Okay, I think we'll have to stop here. We're going to talk about how you can impact the rate on what's tomorrow? Tuesday. And then I'll try